All right. So last time we finished up, we had done a couple days on implicit differentiation. And I said it was important to know that because implicit differentiation was vital to related rates. Now, related rates is, I say it's one of the harder topics in Calc 1, but we're going to just take it one step at a time. This is going to be broken up into 2 lectures for the topic. We're going to kind of do starter today with this one, and then the next lecture is going to be a lot of the related rates problems. So once we kind of understand the process, then we're going to move into practicing it. But first, let's review implicit differentiation. Now, there were 2 points here that we could have went with. I just opted to go for this one. So remember, the first thing that we got to do is we're still taking the derivative with respect to x. So first thing we're going to do is we're going to take the derivative of the left side with respect to x. And then we're going to take the derivative of the right side with respect to x. Now remember, when you take the derivative and the variables don't match, we're doing a chain rule. So if I do this one, I'll try and make sure I mark it. So I'm going to do this for the first one, and then it's just going to be understood what we're doing afterwards. So remember, these two do not match. So what I can introduce to actually make this work is if I multiply the top and the bottom by, or not multiply the top and the bottom, if I multiply by 1, but I make my 1 dy dy, or dy over dy, I should say, what I've done is now I can swap these two around. And when I swap these two around, now I just have the derivative with respect to y of y to the fourth times dy dx. Now we know how to take the derivative of y to the fourth with respect to y. That just leaves us, if the computer will cooperate, 4y cubed times dy dx. So that leaves us on the left side with 4y cubed times dy dx. And that's going to equal, now we're going to take the similar approach on the right hand side. If I do that, I'm going to get, so remember, this derivative gets distributed. So if I take the derivative of y squared with respect to x, I have 2y, because we're kind of doing like we did with the y to the fourth derivative. And then it just gets multiplied by dy dx. We don't change anything else. That's just all we do. Now, the next part's easy because we have the derivative of negative x squared with respect to x. Those variables match up, which makes it a lot easier because now I can just say, well, that's minus 2x. And because the variables match, we don't have to have like a dx over dy or something like that. However, we do now have to do the second part, which is I need to collect my dy dx terms, which means I need the derivative with respect to everything with a dy dx on one side and everything without it on the other side. So what I'm going to do here is I'm going to subtract 2y dy dx from both sides. And now when I do that, that leaves me on the left-hand side with 4y cubed dy dx minus 2y dy dx, and that equals negative 2x. So then what we need to do, actually, I'm just going to change this now. We're not going to find it at a particular point. We're just going to find what it is because it's just going to be a plug and chug at that point. So this is going to become dy dx. That's going to be factored out. And so we'll get 4y cubed minus 2y, factored out just like you would any variable, equals 2x, or equals negative 2x, sorry. Then you divide both sides by 4y cubed minus 2y, and you get that dy dx is equal to, if I can write it correctly, we get that dy dx is equal to negative 2x divided by 4y cubed minus 2y. And that would be your final answer. Oh, negative 2x. So, step 1, take the derivative with respect to x of both sides. You may have to do some implicit. The implicit part, remember, comes from the fact that it's not just y equals a function of x. It's x's and y's kind of mixed together. So then, take the derivative with respect to x. Once you've done that, collect every term with a dy dx on one side and every term that does not have a dy dx on the other side. Factor out dy dx, and then divide out the remaining term, or the term that's multiplied by it, and then you have your final answer. So with that, we can go on to our kind of overview of related rates. So what we're going to do is assume we have a relationship among some quantities. And we're going to use implicit differentiation to derive and solve for these relationships. Now, the reason I say it like this is, well, a lot of times you have like an x and a y component and they're changing. However, you don't have a good way to, but let me say this. X may be changing one way, y may be changing the other, but they're both changing as time goes on. So you don't get to just say dy dx. You end up with a dy dt and then a dx dt or something like that. So this is why it's really important, what do you take the derivative with respect to? So let's go just to the volume of a cylinder. Now, it may start out something like this. And as it goes on, maybe the radius is increasing, but the height shrinking. So you end up with something that's maybe more like this after some time has passed. So this is a case where as time went on, your two components changed differently, and they move independently of each other. So it's not just a case of, oh, well, the radius changes with respect to the radius. No. Or the height's constant. This, you could have a chance, or not a chance, but you could have a moment where they're both changing. So the volume is something that can change. Do you remember pi is a constant? It doesn't change. The radius could be changing and the height could be changing. So as time goes on, that's what the little picture here illustrates. Again, I'm not an artist. This is why I do math problems. What's happening is, as time goes on, the radius could increase or decrease, and then same for the height. It could increase or decrease. Or Maybe the radius expands, but the height doesn't change, or vice versa. So our derivative is actually dependent on 4 different variables here. So the volume, maybe if the volume was constant or something like that, we don't know. But the key thing is, notice we have the radius and the height, but we also have the rate of change of the rate with respect to time and the rate of change of the height with respect to time. So let me show you what the derivative with respect to time would be. So if we take the derivative with respect to time of both sides, now remember, I'm going to skip over a little piece of it. dv dt, or the derivative of the volume with respect to time, is just what it sounds like. dv dt. Because if we think about this, what's the derivative of v to the first power with respect to v? It would just be 1. So then if we do this derivative, we now have a product rule. You factor pi out, and we get the first, so r squared, times derivative of the height with respect to time is going to be dh dt, and you can say times 1 if you want to, and then plus the height times, now the derivative of r squared is going to be 2r, and then remember the variables don't match up, so it's going to be dr dt. So what we have is that the rate of change of the volume with respect to time is, if I multiply the pi in, pi r squared times dh dt plus, if I do a little arranging, 2 pi rh times dr dt. So you can notice some other formulas creeping into here. So pi r squared, so of course that's the area of the circle, times the rate of change of the height. So you kind of see how these things interact together. So what we're going to do is try and keep that in mind and say, okay, well, how do all these different pieces interact together? What can I learn from them? And things like that. So let's say we have this next problem. So you have a rectangular area. The width is changing in time. Now read the problem very carefully. How must the length change to keep the area constant? So this is where you have to be extremely careful in reading your problems. To keep the area constant. So if we do this, we have to treat area as if it's constant. Area could be a variable because, the area could be changing, but in this case, it's a constant. Now, sometimes you will be given that information and you don't want to pass it over. Like might say the radius changes, but the height stays constant, or everything is changing but the volume, something like that. There's little pieces of wording like that you have to be very careful about. So if we were to take the derivative of the area with respect to t, not taking into account that the area was constant, we would just get the first times the derivative of the second plus the second times the derivative of the first. So we have the width times the rate of change of the length plus the length times the rate of change of the width. Now, if the area is constant, like we said, that means the derivative is 0. So remember, we want to know the width is changing, and what we're after is how the length has to change. So our length changing is here. That's the dl dt. So what we're going to do is we're going to take this formula up here, and that's going to be 0 equals the width times dl dt plus L times dw dt. And now my goal is going to be, I need to get dl dt by itself. So I'm going to subtract L times dw dt over to the left side. So then I'm left with negative L times dw dt, which is equal to w times dl dt. And then, again, last thing to get it by itself, divide both sides by w. So I'll have dl dt is equal to negative length divided by width times the rate of change of the width. And so now what we know is that if we want to keep the area constant, which again means its rate of change is 0, then the rate of change of the length has to be this ratio of the negative length divided by the width times the rate of change of the width as time goes on. And again, the whole point of it's right there in the name, related rates. We have rates of change, and we're trying to figure out how do they relate together. I know it sounds really dumb when I say it that way, but is what it is. So now we know, though, if the length is changing, what do I have to do to keep the area constant? I have to have it be negative L divided by W times dW dt. So the rate of change of the length is equal to the rate of change of the width multiplied by this negative ratio of the length to the width. So let's say in a given scenario we have that the width is 5 centimeters and the length is 20 centimeters and the width is shrinking. Key word there. Shrinking at 0.2 centimeters per second. What is the rate of change of L? If I click the right button, then we would have dl dt is equal to, just plug in the values, negative 20 divided by 5 times, now because it said it was shrinking, we have to keep in mind that means that the rate of change is negative. Not all the time will it say that the rate of change is negative blank or positive blank. If they say increasing or decreasing, you have to keep in mind what that means in terms of what you're dealing with. So if the width is shrinking at a certain ratio, then that gives us that this has to be negative 0.2. And so our rate of change then is just negative 4 times negative 0.2, which is going to be positive 0.8. Let me make the multiplication sign not look like it's negative 4 point negative 0.2. There we go. So that gives you an idea of how the related rates work together in this particular problem. Now again, key things here are implicit differentiation is being used throughout. You don't, well, I won't say you don't ever, but in these cases, none of the variables that we have, so the area, the width, the mixture of width and length is the width. The area, the width, and the length are all changing with respect to time. None of these problems have the area is changing with respect to the width. or the length. It's always these rates changing as time goes forward. So do keep that in mind. Now, what about an application? Well, let me talk about the strategy first before we do an application. So first thing, understand the problem. Now, once we start doing some of these, more of the application problems, drawing a sketch. Again, I'm no artist. I struggle with stick figures. But if you can get a general idea of of what shape you're looking at, how the problem is going, that's going to make your life a lot easier. Always be careful and name your variables. And then capture the values of the variables. What I mean by that is, well, if you're having to name variables, make sure you're also good to figure out what the variables at the time you're looking at are. So the capture the values is, for the particular instance, what are they? So always identify what you're looking for. For us, this is Calc 1, so probably looking for a derivative, which means you're looking for a rate of change. So always make sure you identify what you're after. So usually for us, like if we go back to this one, what was the, or how much the length change to keep the area constant? We identified that we needed to know what the rate of change of the length was. So this is another thing. Not all the time are all the equations you need going to be given. So you'll see in the next problem what I mean by that. So keep in mind what you're dealing with and do pull on some of that prior mathematical knowledge. You will need it. Sometimes you're going to have to use two equations separately and then bring them together. So maybe you're not given all the information. Maybe you have like an angle, but then you also have a ratio of how two sides of the triangle work. You might have to use that ratio along with the angle to get maybe this particular rate of change that you're after. So be aware of things like that. A lot of times these problems are going to be differentiate with respect to t. Sometimes it may change, but a lot of times we're going to be looking at what's the derivative with respect to t, because a lot of these problems are objects moving through space, moving on a grid, something like that. And use your known values to solve. So if you have your values, plug them in. It'll make your life easier. And then, of course, you never want to get the right answer to the wrong problem. If the problem says, what was the rate of change at this given time, or when the width is this and the length is this, don't just leave it as, I found the derivative. Great. That doesn't answer the problem. You always want to be careful about what was asked. And if it asked for what's the rate of change at this given time, make sure you find the derivative and then plug in the values. Don't just leave it as, I found the derivative, say yay, and move on from there. Sometimes they do want more information. And again, and I think I've stressed this a lot. Make sure you're careful about your units and your signs. Don't mix things that don't go together. If it's acceleration, remember it's the length divided by the time squared. If it's miles per hour, that's a velocity. So keep those things in mind. Like I mentioned before, you don't want to ever mess something up by just saying, oh, it was 30. 30 what? Was it 30 meters per second? What is it? 30 miles per hour? Was it 30 meters per hour? This is like the, I believe it was a Mars rover that was slammed into the face of the planet because going back and forth, meters and feet were not converted. And so that costs millions of dollars. This will cost you a few points, but try and treat it with the same level of priority. So, let's say for this one. So, how fast is a speeder going? In this case, we have the police officer is 60 miles per hour. That's their speed. The police officer is not 60 miles per hour. They are not running at 60 miles per hour. They are driving in their police car at 60 miles per hour. And they're 0.6 miles from a corner. The speeder's going is 0.8 miles from a corner. And there's a 20 mile per hour relative in the radar. So, this is what I mean by drawing a picture and knowing what you're dealing with. Now, the police car is going 60 miles per hour. We're saying that it's relative to this corner. You don't want to have what's the best way to put it? You don't want to line these things up the wrong way. Police car is coming from one angle, so you would treat it that same way. Notice it says dy dt is negative 60 miles per, or is negative 60. That is not saying that it's negative 60 miles per hour. Again, if you go negative, you're going backwards. So, keep in mind your relative speed. In this case, because it's traveling down, or sorry, not the relative speed, because we're treating it as it's going towards the corner, and we're placing this just to make it easier, we're just placing it on your standard XY axis. As it goes down, you have to think that's like the Y value decreasing. So don't think that the car is going negative 60 miles per hour. The car is going 60 miles per hour. But in relation to our map, this is what we have. The car's Y units are decreasing. Now, the thing that we were after is this, the dx dt. Because I want to know how fast the person that's speeding going. So we have the distance between the two vehicles here. We don't know that, but we do know that the relative speed is 20 miles per hour between these two. So that means if you think about this like a triangle, this blue line is currently increasing at 20 units. If we're thinking about it like this, technically it would be 20 miles. Now that's the rate of change at that given instant. So miles per hour. It's, again, though, when you're driving, there's a difference between you averaging a certain speed and you always driving a certain speed. Just because your instant rate of change at one given time was 80 miles per hour does not mean you travel 80 miles per hour all the time. So we have the police's position and their speed. And again, their speed is 60 miles per hour, but in the context of this graph that we've created, they're a negative, or they're a decreasing in Y units. And then we have the speeder's position and their speed. Now again, notice here, I'm going to redirect your attention. The Y is 0.6 because we said they're 0.6 from the curve, or from the corner, sorry. So this distance here is 0.6. And then similarly, this distance is 0.8. Now, if I could draw a straight line, that would make it a little bit nicer. So this is where I talk about, or this is what I meant earlier when I said you're not always going to have all the given information. In this case, we don't have anything else. This is all that was given. these three little lines. What we then did was just say, okay, well, let's put it on an XY plane because we can kind of translate it pretty well. But now that we're here, what we need to keep in mind is, what tools do I have available? Well, this is a corner, so I know this makes a right angle. Because that makes a right angle, we can actually use some of our formulas we know. So we have a right triangle, so I'm going to use the Pythagorean theorem. So that's going to give us s squared equals x squared plus y squared. So now, notice we have a formula that uses all of our components. Now it's just a matter of putting them together. So remember, we're after dx dt. So now what we've got to do is, well, I need to take the derivative of the whole term, or of both sides. And this one's all nice because if I take the derivative with respect to t, all these are just a variable to the power of 2. So each one is going to be, so the first one is 2s times ds dt. And then all the rest are going to follow a similar pattern. 2x dx dt plus 2y dy dt. Now, I'm going to divide out the 2 just to make this a little bit easier. But then I'm also going to subtract this y dy dt term. So again, I'm going to divide out 2, and that's going to give me s ds dt equals x dx dt plus y dy dt. So if I subtract over dy dt, I get s times ds dt minus y times dy dt, and that equals x times dx dt. Now, last thing to do to get dx dt by itself is just divide x from both sides. So we get dx dt is equal to s times ds dt minus x times, or not x, sorry, minus y times dy dt, all divided by x. Now again, you don't want to get the right answer to the wrong problem. If it just said, what's the derivative? Congratulations, you're done. But it didn't. It said, how fast is the speeder going? So now what we have to do is determine whether or not, or not whether or not, we have to determine what is the value of that rate of change. Now, there's something I could have done at the start that would have worked, but I didn't want to do that just because it would create a major chain rule problem. So what I wanted to avoid doing was solving for just s and making this like s equals square root of blah, blah, blah. Because then, again, you have to do the derivative of something inside of a square root, which is going to make a slightly messier equation. However, for this problem, if we go through, then I also would know that s is just equal to x squared plus y squared. So then this can substitute here. So then I'm left with dx dt is equal to the square root of x squared plus y squared times ds dt minus y times dy dt. And then all of that's divided by x. So now we actually know all the values. The problem was beforehand, I know ds dt is 20. I know the x value. I know the y value. I know the dy dt value. But I didn't know s. And now we have this s value in terms of... we have the s value in terms of x's and y's. So now we can just find out what the value is. So if I plug everything in, you'll have to forgive me for having to write it up here. Dx dt is going to equal the square root of 0.8 squared plus 0.6 squared times ds dt is 20 minus y, which is 0.6, times dy dt, which is negative 60. And then all of that is divided by our x value, which is 0.8. And if I had been smart, I would have actually written this down before the problem, instead of having to calculate it by hand. So 0.6 squared plus 0.8 squared and that's multiplied by 20. And then minus 0.6 times negative 60. And then divide by 0.8. And as long as I did my math correct, that should be 70. And again, don't forget your units. You don't want to be slamming spacecrafts into Mars. So it's 70 miles per hour. And that's how we go through the problem. So any questions on that one, just shoot me an email or let me know. So we'll have... So what's the best way to put it? Let me go through it one more time. First thing we did, and I'm going to do this. I'm going to say, or I'll mark these in, let's say purple. So first thing we had, so this was the what do you know. The police is going 60 miles per hour. They were 0.6 miles from the corner. Speeder was going 0.8 miles, or the speeder was 0.8 miles from the corner, and we had a 20 mile per hour relative for the radar. This was the... I guess I should have identified this first. What am I looking for? So in this case, what I was looking for was how fast is the speeder going. Then we had to identify, I will call these our components. So then we identified our components. We had the distance between the vehicles, the relative speed, the police position, the police speed, and then the speeder's position, the speeder's speed. This over here was the draw a picture / sketch. And it just gave you an idea of what am I looking for? And it kind of put it in context. So then once we were at this point, so this here, this was kind of the what other formulas are useful. And so again, we didn't have an actual formula. We just knew those three things at the top. And then we drew a sketch, and then we identified our components, and from there we said, oh, hey, we made a right triangle. And because we made a right triangle, we can actually work with that. And once you work with it and go through it, everything turns out pretty good. And again, the last part, answer the question. It didn't ask, so down here, so find a rate of change. Now, typically with related rates, that's what we're doing. We're looking for a particular rate of change. In this case, it was how fast is the speeder going. That was our rate of change. So this is the first example problem. Next lecture is going to be just a lot more examples because these are hard, and math's an active sport. You don't get better at it by watching other people do it. So these do take some practice. So these are the homework problems that I recommend right now. The practice, just some extra ones that might be helpful, but mainly focus on the 3.8 homework and give these a shot, and then come into the next lecture and we'll just do a lot more practice. So I'll see everyone then.